Hey everyone! Today, we're going to jump into a real classic from EAI Irodov's famous problem book, Problem 1142. You know, this one's a fantastic workout for your physics brain because it really ties together work, rotation, and energy in a super elegant way. All right, let's get into it.
So here's the setup. Picture this. We've got a small sleeve, mass M, and it can slide without any friction along a rod. The rod itself can pivot around its end, point A. Now this sleeve is hooked up to the pivot with a spring. When everything's just sitting there, the spring has its natural, relaxed length, which we'll call L0. The big question is, how much work do we have to do to slowly get this whole thing spinning up to an angular velocity of omega?
Okay, hold on. Before you even think about writing down an answer, I gotta put up a big warning sign. Look, I know what you're thinking. Work equals change in kinetic energy. It's tempting, right? But that's the #1 trap with this problem. It's wrong, and we're going to spend the next few minutes understanding exactly why.
So here's our game plan to get this right. First, we'll talk a little more about that pitfall. Then we'll figure out what this system actually looks like in its final spinning state. After that, we'll bring out the big gun, the work-energy theorem. We'll use it to calculate the energies, and finally we'll put it all together for the answer and talk about the key lessons learned.
All right, let's start with that mistake that's so easy to make. You put work in, something starts moving, so you get kinetic energy. It feels so intuitive to say work equals final kinetic energy, but that's only looking at half of what's really going on here.
Right. Here's the question you have to ask yourself. When this system is spinning, that sleeve is trying to fly outwards, isn't it? It's being flung out. Well, what's holding it back? The spring. But for the spring to pull back, it has to stretch. And a stretched spring, what does it have? It has stored potential energy. So the work you do isn't just creating motion, it's also being used to stretch that spring. That's the other half of the story.
Okay, so before we can even begin to calculate energy, we have to know what our system looks like at the end. When it's spinning steadily at that angular velocity omega, where's the sleeve? What's the new length of the spring? That's our first real task, finding this new equilibrium.
This lays it out perfectly. When it's at rest, nothing's happening. No net force on the sleeve, so the spring is just chilling at its natural length, L0. But once it's rotating, you've got this outward centrifugal force pulling on the sleeve. For the sleeve to find a stable position and not just fly off, the inward pull of the spring has to grow to perfectly balance that outward force, and that means the spring has to stretch to some new longer length, which we're calling L.
And it all boils down to this one simple idea. From the perspective of the rotating sleeve, it's not accelerating outward or inward. It's stable. That means the forces on it have to be balanced. The spring force, pulling in, must be exactly equal to the centrifugal force pushing out.
Now we just need to put some math to that idea. We know from Hooke's law that the spring force is its stiffness, kappa, times how much it is stretched, which is its new length, L, minus its old length, L0. And we know the formula for centrifugal force is m omega squared times the radius of rotation, which is simply L. We set them equal and boom, we have our equation.
Now, with a little bit of algebra, and don't worry, it's pretty straightforward, just get all the L terms on one side, we can solve for L, that final length. This expression right here is super important. It tells us exactly how far out the sleeve is when the system is spinning. Go ahead and tuck this result away in your back pocket. We're definitely going to need it very soon.
So we have the final state. Now how do we find the total work? We need a tool that can handle all the energy changes, not just the motion. And that's where we bring in the master key for problems like this one, the wonderful work-energy theorem.
What the work-energy theorem really tells us is that the net work you put into a system doesn't just vanish, it has to go somewhere. It becomes the change in the system's total mechanical energy. And total energy means everything. Kinetic energy, yeah, but also any potential energy. It's the whole shebang. This is exactly the tool we need to avoid that pitfall from the beginning.
So this gives us a perfectly clear 4-step plan. We'll find the initial energy, then we'll find the two parts of the final energy, the kinetic and the potential. Finally, the work done is just the total final energy minus the total initial energy. Simple, logical, and it guarantees we won't miss anything.
All right, let's get to it. Time to actually calculate these energy values. We're just going to assemble the pieces of our puzzle one by one.
Let's start with the easiest one. In the beginning, is anything moving? Nope, so kinetic energy is 0. Is the spring stretched or compressed? Nope, it's at its natural length, so potential energy is also 0. That means our total initial energy, E initial, is just 0. Easy enough.
Next up, the final kinetic energy. We all know the formula, 1/2 mv squared. But what's v here? Well, for an object in circular motion, its linear speed v is just its angular speed omega times the radius, which for us is that final length L we found earlier. So we just plug that in, and our kinetic energy is 1/2 m times the quantity omega L all squared.
And here it is, the part we can't forget, the other half of the story, the final potential energy stored in that stretch spring. The formula for that is 1/2 kappa times the extension squared. And the extension is just the final length L minus the initial length L naught. This is the energy that went into physically changing the shape of the system.
Okay, we've basically done all the heavy lifting. We've figured out the final geometry of the system, and we've calculated expressions for both the final kinetic and potential energy. All that's left is to put them together.
Since our initial energy was 0, the work energy theorem makes this really simple. The total work done is just equal to the total final energy. And that's just the sum of the final kinetic energy, T, and the final potential energy, U. And there it is. That's our answer. You can see it clear as day. The work went into both creating motion and stretching the spring.
So what's the big lesson here? First, always remember, work changes the total energy of a system, not just the kinetic part. Energy can hide in different forms, like motion or, in this case, the configuration of a spring. And for any problem involving a final steady state, your very first step should be to analyze the forces to figure out what that final state actually looks like.
Okay, I want to leave you with a little something to chew on. The problem very specifically says the system is spun up slowly. That's a huge clue. What do you think would happen if we spun it up instantly instead? Would the work needed be the same? More or less? Think about it. What else might happen to the energy if things get shaky? That's a great question to puzzle over. Thanks for joining me.